Okay, we'll start our presentation. So thank you for joining Stantec's technical webinar on PFAS and the energy industry. My name is Bob Wilson and I will be your host today. Before we get started, we got a couple of housekeeping items. First of all participant audio will be muted during the presentation. Your sound may be better on a headset, but that's not required. If you have a question, please type them into the questions panel on your webinar dashboard. Questions will be answered at the end of the presentation. Today's webinar is being recorded and a copy of the presentation and the supporting materials will be sent to you afterwards. This includes a form that you can use to capture continuing education credits if needed. So those of you who are familiar with Stantec, you know that safety is critical to our business. We start every meeting with the safety moment. Since we're approaching the spring season, our safety moment is on the top 10 safety cleaning tips. Top 10 spring safety cleaning tips, I'm sorry. So on the screen, you'll see the top 10 spring cleaning safety tips. But the one that really resonates with me is number 3. Being safe while on ladders and step stools. This reminds me of my neighbor who lives on the street next door, and he fell off his ladder while putting up Christmas lights. He was actually a fireman, and he was not only severely injured, but he was actually very embarrassed when he was helped by the fire department that he actually works for. My wife actually saw this take place. So now she is actually very happy to help me with whenever I use a ladder in the yard or working at home. So please make sure you have a spotter. So moving on, here's a little background on our presenters. Dr. Krista Barfoot has over 25 years of contaminated sites experience and specific expertise in emerging contaminants related to investigative and analytical approaches, risk assessment, and remediation of PFAS. Her PFAS project experience to date includes AFFF release sites, waste management sites, and brownfields. Dr. Angus McGrath has over 28 years of experience and is a national technical leader for remediation at Stantec. He's a recognized leader in the petroleum industry with respect to environmental geochemistry and remediation. He's been involved with many PFAS projects across the U.S. and is developing plans for remediation at several sites in response to California's initial PFAS regulatory assessment requirements. And then Mr. Joel Thompson has over 25 years of industry experience and is a national technical leader for quantitative hydrogeology at Stantec. He's an expert in hydrogeology, groundwater and LNAPL flow modeling, contaminant fate and transport, and the development of site conceptual models. All 3 of these experts participate in various industry technical groups, including the Interstate Technology Regulatory Council PFAS group. And with that, I will turn it over to Krista.
Thanks, Bob. I just want to start today by noting that while you have Angus, Joel, and I speaking with you today, we are just 3 representatives from Stantec's PFAS working group that's comprised of over 100 technical staff with PFAS expertise here at Stantec. And at the head of this group is Jack Angelo, who you see pictured here with us, who not only leads the PFAS working group and our research group here at Stantec, but he's also an adjunct faculty member at Johns Hopkins University's Bloomberg School of Public Health in the Department of Environmental Health and Engineering. So Joe is also a very important part of Stantec's PFAS team. So we'll start today with a quick introduction on some of the basics around PFAS, and then look specifically at why PFAS may be relevant to the energy industry. From there, we'll touch on some of the important fate and transport aspects associated with these parameters and run through the various remedial options that are currently available. And we'll finish by just quickly touching on some potential changes we may see with respect to fire suppression systems going forward, and run over a couple of case studies before opening it up to questions. So let's talk about PFAS. And you've probably heard of PFAS or per and polyfluorinated alkyl substances before. because it does show up in the news every now and then when environmental releases are discovered. And PFAS has even found its way into the world of entertainment, having been featured in the Netflix special called The Devil We Know, and the movie called Dark Waters, which was released to theater in November of 2019. PFAS has also been in the news over the past few years as it has been the center of a number of large litigation settlements, currently already totaling over $5.5 billion across various US states, with the largest settlement to date being a $4 billion settlement that was reached just in January of this year, and that was in relation to PFAS discharged into the Cape Fear River. In fact, an article appeared last September in the Insurance Journal noting PFAS as the top emerging litigation risk. So what is PFAS? Well, PFAS are a suite of human-made aliphatic substances that contain the perfluoroalkyl moiety and some kind of attached functional group. These parameters have been manufactured and widely used in industrial applications since about the 1940s to 50s, often as surfactants given their amphiphilic properties. So they've been broadly used as heat, oil, stain, and grease-resistant coatings on things like clothing, furniture, food packaging, and other products. And they've also been widely used as fluorosurfactants, especially in the production of aqueous film-forming foam, or AFFF as it's typically called. In fact, if we look across all the different industries that have recorded uses or handling of PFAS within their processes, you see it's very wide-ranging. And so it should come as no surprise that we find PFAS within many of our commercial products. Now, because all it takes to be a PFAS is a perfluoroalkyl moiety and some kind of attached functional group, as you can imagine, there are thousands of possible parameters that could be PFAS. However, there are really only two that are considered common, and that's perfluorooctanoic acid, or PFOA, and perfluorooctane sulfonate, or PFOS. These two parameters were most commonly used in manufacturing and are degradation end products for a variety of PFAS precursors. So these two parameters are the most researched and thus the best understood, and so not surprisingly also the most regulated. In fact, you've probably started to notice there are various commercial products that now like to boast in their labeling that they are PFOS-free or PFOA-free. But I want to note that certainly does not mean that those products are PFAS-free. Now, the various properties of PFAS that make them so attractive for use in industrial processes are also the properties that make them so challenging to deal with once they're released to the environment. One of the key properties of issue is that the carbon-fluorine bond that is so prolific within these molecules is the strongest covalent bond in organic chemistry. This means that when PFAS are released to the environment, they experience no biotic or abiotic degradation under natural conditions. In fact, the only widely demonstrated destruction process for these parameters to date is still thermal destruction at very high temperatures. This means that when PFAS are released to the environment, they are very stable and persistent. And since they are also soluble, they can also be highly mobile and thus tend to demonstrate long-range transport. And this has been observed with a wide range of PFAS being detected in environments, wildlife, and humans around the world. In terms of why this widespread exposure may be important, it really comes down to toxicity. And there have been some limited human toxicity studies completed, and of course a larger suite of animal studies, generally focused on those two very common PFAS, PFOS and PFOA. And while the specific observed results in terms of effects have varied across these different studies, the overall conclusion has consistently been that exposure to PFOS and PFOA can negatively impact human health. So in response to this, what we've seen at an international level is governments establishing guidance and screening levels specific to various PFAS. Of note in the US, we've seen a lot of leadership at the state level, with 24 states having established some kind of guidance level for PFAS, and 17 of those states even having regulated values for up to 16 different parameters. You'll also notice from the slide, there's been a lot more focus on setting guidance levels for water versus soil. And that's because since concerns first arose regarding PFAS, the primary exposure pathway of concern has been, and still remains to me, ingestion of PFAS via drinking water. So we can take a quick look at some of the criteria that has been established internationally for drinking water. And what you'll see is there is a wide range in the values that are understood to be protective of human health, in some cases ranging by orders of magnitude. You'll notice there are also different ways agencies are setting their values. In some cases, they are setting a concentration that is specific to a parameter, but in other cases, they're setting a concentration that is to be compared against the summation of a suite of PFAS ranging from 2 up to 12 different parameters. I also want to draw your attention to the values we see here in California as the notification levels, as these are currently the lowest values established and they are rubbing up against the limits of analytical detection. So we are seeing values being set by different agencies that are very much pushing the limits of our current analytical capabilities. It's also worth noting that in the US we do have a federal value, but there are also state values, and the federal value to date is still not regulated, but many of those state values are. We can also take a quick look at the values being set for soil at an international level. And again, you see a wide range, often by orders of magnitude, and the criteria being identified as protective of human health. Now here, some of the variation you see is due to the exposure pathway that's being considered in developing that criteria. So in some cases, you can see it's direct contact, while others it might be through ingestion of PFAS through consumption of garden produce, or it's related to the protection of drinking water. And interestingly, the lowest values here are still being driven by protection of drinking water. Now, all that said, there are a few things that are really important to keep in mind when we talk about health risks associated with exposure to PFAS, because there is still a lot of uncertainty associated with our understanding of PFAS toxicity and the risks associated with exposure. First, we are relying heavily on animal toxicity studies to understand these risks, and humans and animals certainly do not always process chemicals the same way. We are also relying heavily on research that is specific to those two most common PFAS and generally assuming similar types of results for other PFAS, which may or may not be appropriate. So ultimately, the bottom line is that more research is needed in this area, and as that research is completed, we can expect to see these guidelines and target concentrations continue to evolve. And given that we are currently butting up against the limits of analytical detection, it's also important to consider what this means in terms of sampling for these parameters, especially given that PFAS are prolific in commercial products. So there is a specific need to develop sampling programs that will guard against the production of false positives during sampling due to the inadvertent introduction of PFAS within the sampling train itself or just through the sampling process. That said, PFAS do also tend to adsorb rapidly to various surfaces, so there's also a need to guard against the potential for low bias of data in developing the sampling program. So there's really a lot of care needed in designing a sampling program that will facilitate the production of defensible and reliable data. And you can consider then what these really low target concentrations and the potential for low or high bias in the data might mean when we start looking at trying to develop remediation programs, and we'll come back to that in a little bit. So for now, we can have a look at why PFAS may be of relevance to the energy industry. And if we circle back to the various industrial sources of PFAS we looked at earlier, there are three specific places we see the potential for the energy industry to intersect with issues related to PFAS. First, there is the potential for PFAS-containing surfactants and evaporation inhibitors to be used within the production process. And if we see the use of PFAS-containing chemicals in production, we may also reasonably expect to see it being released from these facilities within the industrial wastewater. And while industrial wastewater may undergo some kind of treatment process, it's rare these facilities would have treatment specific to PFAS, and so we could expect PFAS to potentially just flow through the treatment facility and simply be released to the environment. A possible third source of PFAS release at an energy facility could be through the use of PFAS-containing aqueous film-forming foam, or AFFF, within the fire suppression systems at these sites. Beyond the actual use of AFFF to address a fire, the testing and maintenance of these systems sometimes looks like what you see in the picture on the right, where foam is simply discharged to the surface and allowed to dissipate. So this could be another potential source of PFAS release from these sites. In fact, the potential for petroleum and petrochemical production facilities to act as a source of PFAS release to the environment has been formally recognized by the California State Water Resources Control Board. This board has released orders directed towards specific industries that may act as PFAS source sites, including airports, landfills, and chrome plating facilities. And within these orders, it has identified petroleum refineries and terminals, as well as petrochemical production facilities, as other potential PFAS source sites. So it is generally expected that the board will release an order that would be specific to these facilities, potentially in the short term. And this is partially expected just because we see so much activity around PFAS in California. For example, in September of last year, the California government signed into law a ban on the use of PFAS within AFFF, and that ban starts coming into effect January 1st of next year. So this ban will also obviously have some implications for the energy industry for sites that are in California and still using PFAS containing AFFF in their fire suppression systems. So ultimately, in terms of why the energy industry needs to care about PFAS, there's really two management items. From the environmental management side, there is a need to consider the potential for environmental releases from these sites, either through the use of PFAS-containing products in manufacturing or through releases associated with the fire suppression systems at these sites. On the other hand, there is the whole property management issue. Could you have sites where a fire occurred and cleanup was done, but PFAS wasn't considered, and maybe now we'll see new orders against those sites? There's also the element of due diligence in buying and selling properties. Is the potential for PFAS impacts considered in that process, and what does it mean for property values? And finally, another trend we're seeing is in the insurance industry with a movement towards excluding PFAS from insurance coverage. So that could also have implications with respect to property management for the energy industry. And with that, I will turn it over to Angus.
Thanks, Krista. Before we jump into a discussion of remediation of PFAS, let's summarize the properties of PFAS that influence remediation. Given the wide variety of PFAS, it's not surprising that they collectively exhibit a wide range of different physical and chemical characteristics that can affect their behavior in the environment and our ability to remediate them. As described by Krista, the properties of PFAS have a strong influence on remediation. These compounds are highly persistent because of the strong carbon-fluorine bond, meaning that they are difficult to chemically destroy or biodegrade. They can be highly mobile because of the polar and non-polar portions of their chemical structure, but generally have poorer absorption characteristics because other compounds can absorb more effectively than they do. On top of that, because of their extremely low cleanup levels, PFAS pose a significant challenge for remediation. Co-contaminants, which typically are present at concentrations orders of magnitude higher than PFAS, can significantly influence PFAS remediation, fate, and transport in the environment. So looking at fate and transport at oil and gas sites, well, at oil and gas sites, PFAS mobility can be influenced by commingling with free-phase petroleum hydrocarbons in the form of light non-aqueous phase liquids. PFAS absorb and accumulate along the petroleum hydrocarbon NAPL water interface, partitioning into the L-NAPL, both in the vadose zone and the saturated zone, increasing PFAS accumulation in the L-NAPL zone, increasing the retention and retardation of PFAS potentially, and leading to greater persistence of PFAS in the environment. Furthermore, changes in the geochemistry by these commingled petroleum hydrocarbons may inhibit aerobic degradation and support anaerobic degradation, leading to changes in the mineral phases that are important for absorbing some of these PFAS because they are also polar. So now let's transition to talking about remedial options. We will start the remediation discussion with the proven ex situ existing technologies for water treatment. For some background, an example comes from the Orange County Water District, who determined that 71 out of 200 drinking water wells operated by their partner companies exceed the new response levels of PFAS and PFOA promulgated by the Regional Water Quality Control Boards. That's approximately 35% of the operating drinking water wells in a county that depends on groundwater for drinking water. Currently, their best options are granular activated carbon and ion exchange. These are adsorption materials, and they're both single use for drinking water, meaning that the spent media is incinerated and disposed of or regenerated for other industrial purposes. The reject and waste media requires incineration or landfilling. There are no commercially available destructive technologies that are generally accepted except for incineration, and incineration requires temperatures greater than 1100 degrees centigrade. The next group is filtration, and this includes reverse osmosis and nanofiltration. They require pre-treatment for mixed wastes like what we see at a refinery site or an AFFF fire where petroleum hydrocarbons were present. And they don't reach regulatory limits, but can be used in combination with GAC or resin, that's granular activated carbon or ion exchange resins, extending the lifetime of the sorbent, generating a concentrate solution that, along with the GAC, requires incineration. Next, there are several types of coagulants that, or sorbents, and these coagulants will precipitate the PFAS, and that precipitate can then be filtered out and incinerated. The treated water will then need to have some form of GAC or ion exchange treatment to meet effluent standards. What's good about these coagulant treatments is they aren't susceptible to co-contaminants such as petroleum hydrocarbons and other things, for instance, found at landfill leachate. And therefore, they are more effective as a pre-treatment for GAC and ion exchange and reverse osmosis for removing higher concentrations of PFAS. So this bottom box down at the second part of the table talks about technologies that are in development for either destructive technologies like electrochemical oxidation, which is intended to completely destroy the PFAS, or ozone fractionation, which precipitates out the PFAS. So next, let's look at in situ opportunities for treatment. Here again, we're going to focus on groundwater with some discussion of soil first. So our first grouping again is uses activated carbon. The material in this case is powdered activated carbon. Plume stop is an example of that. It's been shown in pilot studies that particulate powdered activated carbon it can be highly effective at absorbing and stopping PFAS migration, although it will saturate over time, and TLC will total organic carbon can displace the PFAS. Second on the list is sorption, another sorption technology, this one called Rembine, which can also be attached to a permeable reactive barrier that will absorb the PFAS as groundwater migrates through. And then the last on that list is the granular activated carbon, which can be created, put in place as a barrier, and it's a little less efficient than the powdered activated carbon, but can form a barrier nonetheless. And finally, we talk about soil treatment in the form of thermal conduction heating. PFAS removal from the vadosone soils, where you can get temperatures up to 350 degrees centigrade, can remove the PFAS as you're volatilizing off the water. So that can be an effective treatment for soils. Now transitioning to what can we do at refineries for AFFF PFAS fire response to mitigate the contaminants that are generated by a fire, for instance. Well, one of our clients asked us whether we could put together a treatment train, a hypothetical treatment train, using available technology to treat the soil and groundwater generated, or surface water also generated by a fire. This hypothetical treatment train at the top uses conductive heating for the soil treatment. And then the water generated from the conductive heating can either go to incineration or can go to a coagulation treatment, which will further concentrate the PFAS, which then goes on to incineration. The second treatment train in this, at the bottom of this slide, is just for PFAS water. Here, PFAS water is treated with a coagulant again, and then the low PFAS water goes to either granular activated carbon or ion exchange for final polish. This treatment train could be highly effective for treating, for instance, AFFF contaminated water at a fire site. So next, let's just talk briefly about thermal conduction heating. Thermal conduction heating can be highly effective. If you can achieve temperatures in the vadose zone or ex situ up to 400 degrees Celsius, then you can expect 99% removal of PFAS and PFOA after 2 weeks at 350 or at greater than 350 degrees centigrade. So if you couple this then for the vapor treatment with either coagulation or incineration of the vapors that come off, this is a highly effective method for treating soils. If we go to the next section, here we talk about coagulation for water treatment technology. Well, if you have a mixed waste, the coagulant, as I said, can remove up to 99% of the PFAS from water, and it that adding a flocculant like ferric chloride dramatically improves the removal using these coagulants for treatment. And the next slide just shows you here the mobile coagulation treatment system, a typical layout for that, with mixing, high efficiency flocculation, filtration, and precipitate waste incineration and the precipitate, goes to waste incineration. This would need GAC polishing to get the water coming out of the system to be able to be discharged. For in situ treatment, in the following slide, as we talked about, this colloidal powdered activated carbon is one of the best treatments. Now, just to be clear, it is highly efficient, but it has some limitations, and those are that it really works best on low to moderate concentration plumes, and TPH, total organic carbon, and some natural organic carbons can interfere with absorption. So now let's transition to another question that's arisen given the changes in laws, for instance, in California, and that is AFFF replacements. Just to speak to this generally, right now there are a number of chemical alternatives to replace AFFF, high expansion foams, fluoroprotein foams, these self-expanding foams, and fluorine-free foams. What the feedback we've received from our clients and their fire chiefs at refineries is that the fire chiefs have less confidence in the non-PFAS AFFFs for treating Class B liquid petroleum fires. And so because of that, they are tending to stick to PFAS AFFF for the time being. In California, the law stipulates that PFAS need to be eliminated by 2024, but there's actually a provision in the law that allows refineries and terminals to use AFFF until 2028. And if they find that they need it beyond that point, they can petition to continue use beyond that point if another alternative that they believe is adequate hasn't been found. So then there are also here non-chemical alternatives like flammable drainage floor, liquid drainage floor assemblies. But when you're looking at the replacement systems, there's some considerations you should take into account. Is the technology an effective firefighting measure? What infrastructure upgrades will be required? Is the product NFPA approved? And it also, does it meet local code official requirements? So along with AFFF replacement comes also, as we see in the next slide, PFAS AFFF equipment cleaning. One method that's been shown to be highly effective is a coagulant flush. And here you see in this slide an example of a fire truck being treated for PFAS, where the pumping systems, the tanks and everything are flushed with and rinsed with this coagulant. The coagulant removes the PFAS compounds. PFAS compounds tend to be they're very sticky to surfaces. So having these coagulants helps reduce that effect and remove them from the water and the equipment. And then that water gets treated in the system that I showed you earlier, and the water then gets a final GAC or ion exchange treatment for its before its final disposal. Now let's transition to a refinery case study. As you know, PFAS is used in AFFF. This is a representation of AFFF impacts at a fire training area at a refinery site. The two rectangles shown on the slide here represent the fire training building and shed at the site. And then what we see here with the two blobs, the blob on the left shows the area with the highest PFAS concentrations in soil, and the right smaller blob shows the highest concentrations in groundwater. This case illustrates one of the unique characteristics of PFAS. The center of mass in soil within the vadose zone will not necessarily be co-located with the center of mass in groundwater. In the next slide, we see the difference in the distribution of PFAS and soil versus groundwater. Furthermore, the composition of PFAS, because there are many different PFAS in AFFF, for instance, is different at the two locations, be it soil and groundwater. And here you can see that predominantly the longer chain PFAS tend to absorb and stick to the soils, and the shorter chain PFAS tend to be more mobile and in the groundwater. As a result, you can't track the source of the plume as easily forensically, for instance, by the composition of PFAS present in soil and groundwater, because they're expected to be different and often and typically are. This is a representation of PFAS distribution and groundwater surface water on the left, on the right, and soil on the left from the fire training area. And you can see that the distributions are not very helpful for identifying the source. So this is a precursor to now hand it off to Joel Thompson, who will provide you an AFFF case study.
Yeah, thanks, Angus. So I'm going to walk you through a case study that provides some real world examples of the challenges surrounding an investigation of the fate and transport of PFAS and the messaging around communication. This case study looks at the historical use of AFFF at a federally owned facility that was used to test fire suppression and combustion properties of building materials. And processed waters potentially containing AFFF were possibly discharged to the paved area outside the building, and that's believed to be the source of PFAS in soil and groundwater. So on the left here, you can see a figure of an aerial photo of the property prior to the investigation, and then on the right, you can see that same area with a disturbed area showing the interaction of a soil removal of PFAS impacted soils. So both the investigation and the communication approach was largely influenced by both stakeholders and media perception. Residents adjacent to this property used shallow groundwater as their primary water supply, and ultimately a class action lawsuit was launched. So with potentially high financial and legal implications tied to the investigation results, the investigation decisions were often made using a precautionary approach. And this approach said that when information is imperfect and decisions are more consequential on one side than that precautionary side influences the decisions that are made. So in this case, many of the early decisions were made to minimize both risk and satisfy stakeholders. I want to back out a little bit and talk about the conceptual site model. So as I mentioned, this was a fire research center. It was in operation since the early 1980s and ceased operation in 2016. As I mentioned, the local residences are on water supply, and those residences are indicated on the figure on the right as the black dots with property and lines. So there's over 50 properties in this relatively rural subdivision. All of them are on their own domestic water wells and septic systems. Groundwater flow direction is indicated by the blue arrow and is primarily to the east, northeast, towards a river, which is a local discharge area. So, this leads us to one of the potential differences in a PFAS investigation is that often risk is driving the decision making early on in the investigation, and so outward in approach is often taken in contrast to a source area outward approach, where you define your source area, delineate the lateral and vertical extents, and then look at potential receptor pathways. In this case, we quickly moved to investigating potential receptors at the water wells to eliminate that risk, and looking at potential surface water discharges. So we took that outward approach, and then as sequential investigations took place, we went back to looking at the fate and transport of the PFAS in the environment, and understanding that to a larger degree once the risk was known for human health risk and environmental risks. I want to touch briefly on the physical environment. So the site down in the right-hand side here shows a block diagram of the site. Generally, the geology consists of a relatively thin, 5-foot thick layer of soil underlain by a dolomitic limestone, which is in turn underlain by Precambrian bedrock. In this case, the groundwater that is being used in the area lies within that sedimentary sequence, with a relatively thin water table, 15 to 20 feet thick, but has large dissolution, secondary dissolution features, which cause groundwater to move relatively fast and to be a relatively productive zone. So contaminants, as I mentioned before, were released at the site, are believed to have infiltrated into the soil, and through that move relatively slowly through this fractured environment, which is poorly connected in the upper part, but once you get down into that secondary porosity-driven area right above the Precambrian bedrock, it moves quite a bit quicker. So so this shows you, both a couple other challenges around a PFAS investigation. Is there often is a primary source, in this case, that original source to soil, and there's often a secondary source. And so in this case, we have pumping wells and septic systems, right? So if the contaminants have made it to these pumping wells and then are discharged again to the septic systems. This is something we've seen in several different sites where the groundwater use and wastewater treatment can often produce a secondary source that also must be investigated and dealt with. Another common feature of PFAS investigations is the importance of surface water runoff and surface water and groundwater interaction. So in this particular site, the site is located at a topographic high, shown there on the figure on the left, or the photo on the left, and groundwater or surface water drains in multiple directions off that topographic high. But the primary direction is towards the north to a local drainage feature, which is an intermittent stream. So water is focused along that drainage feature and allowed to run off the site to the north. But then as that feature intersects that upper limestone bedrock, it is allowed to discharge back into the groundwater. So it's moving through surface water and then back through groundwater. And this is not uncommon in PFAS sites where we've seen contaminants move from groundwater to surface water and back to groundwater, or vice versa. And this figure shows, similar to what Angus was showing previously for the petroleum case study, we're looking at in the upper left of the red box is the on-site source area groundwater concentrations. And you can see that these are the eight of the PFAS compounds that were commonly detected out here. And it's relatively enriched in the 6,2-F2S and PFOS. So the longer chain PFAS compounds. And then on the upper right in the blue box, we're showing that same distribution. And it's relatively in surface water that's discharged north of the site. And at this point, we're seeing then the relative abundance of shorter chain PFAS compounds. And this is not unanticipated given the wide range of physical properties, chemical properties associated with PFAS that have differential sorption properties. And that's what we think that we're seeing here is that the higher organic carbon in that surface water pathway is filtering out some of the larger chain hydrocarbons. And we can see the same distribution in a radial plot to the lower left and lower right, where again you see that typical signature of groundwater in the source area, showing the higher chain hydrocarbon or PFAS, and on the right you're seeing the shorter chain, relative abundance of shorter chain compounds. Now I want to expand that view and look at some of the domestic water sampling that we did at the site. And so as we're looking at these different sources, we can see that there is a pathway that appears to be from the source area in the direction of groundwater flow to several of the domestic water wells, a direct primary source pathway that shows the characteristic enrichment of the longer chain PFAS compounds. What we're also seeing is a secondary source, and we're seeing domestic water wells on the north side of this, sort of the back side of relative to groundwater flow, exhibiting concentrations that look more like the surface water end member. And then in between, as you might expect, you see some of the mixing. So this purple is showing wells that exhibit a mixture that's somewhere between groundwater and surface water, but closer to surface water or closer to groundwater. And then the light blue is showing that same mixture closer to surface water. So this shows another one of those characteristics of PFAS, which represent thousands of compounds. Here we're looking at 8, but have very different fate and transport characteristics, and therefore a different distribution, a signature in the environment. Next thing I wanted to touch on was the idea of uncertainty and the role that plays in investigation and communication. Uncertainty around PFAS can play an oversized role because the science is quickly evolving, and there's much that we don't know about the properties and the environment, the regulatory environment around PFAS. So because risk and uncertainty and trust are inseparable, we need to understand and communicate the sources of uncertainty to effectively manage the investigations. And we can think about uncertainty, sort of group them in 3 ways. The first is parameter uncertainty, and this is something that we typically know from traditional investigations. It's the hydraulic conductivity, the concentrations in the environment, and that can be managed through both additional data and statistical analysis. The second kind of uncertainty is the conceptual uncertainty. It's that understanding, the general understanding of the site, the physical environment, and the fate and transport properties. And again, this is not uncommon for sites, and we can deal with this through either collecting additional data or identifying and filling data gaps. The kind of uncertainty I want to focus on relative to PFAS is that deep uncertainty. This is the uncertainty that's not likely to be reduced during the project life cycle due to collecting additional data. And some of the examples of deep uncertainties around PFAS are the toxicology, as Krista mentioned early on, that there's much that's unknown about toxicology. The regulatory environment, while we see that the concentrations are being established in several states, nearly half the states, that they range over several orders of magnitude, and concentrations seem to be shifting downward. They're not shifting upward, so often changing every couple of years and moving in a downward direction. It's really unknown where that's gonna end up. And then, as Angus was mentioning, there's a few proven remedial technologies, but that's an area of intense research and is quickly changing. So managing uncertainty is really easier said than done. And I just wanted to touch on how we balanced it at the NRC site. Looking at, in the real world where we have limited budgets, we must strike a balance between reasonable effort and the return on that effort. One of the things that I think is important is to incorporate efficient methods. Probably the least efficient way is to collect single point data. So where possible, we're looking at collecting high resolution data. We can collect multiple points across a boring, or looking at things like using geophysics, where we're looking at a cross-sectional view of the subsurface. The second thing is the conceptual site model. In a world where we have deep uncertainties, it becomes even more important to emphasize our understanding of the physical environment, to have a good story to tell that would show that we understand the processes that we can understand, because there's so much that we don't understand. And then just asking yourself what is reasonable. In chasing a plume with part per trillion concentrations and potentially widespread distribution in the environment, it may not be feasible to do an efficient investigation of delineation of the edges of that. And that's where we get back to that outside in approach and looking at eliminating receptors and then going back at looking at the investigation of the plume. So finally, just want to talk again about the communication to the stakeholders. So there's multiple stakeholders in this, as there are in many investigations, but especially in emerging contaminants where the concern can be a significant driver, it's extremely important to build trust with the stakeholders. And once that trust is lost, the challenge of effectively managing a site can be exponentially more difficult. So, looking at the NRC site, we evolved in our thinking from, good science is important and drives the day, to good science and risk communication is the approach to developing a two-way communication approach with the stakeholder engagement, where it's possible to make the stakeholders partners to the degree that it's possible. It's not a one-size-fits-all approach, but where PFAS is prevalent in the media and grabs the attention of the local stakeholders, really need to be understanding how we roll out that idea of risk and the idea of uncertainty. So that wraps up our presentation. Appreciate your attendance, and I'll pass it back to Bob to see if there's any specific questions.
Okay, thank you, Krista, Angus, and Joel. Appreciate that. That was very good. So now we're going to go to the chat box for your questions. So if you have any questions, please type them in, and we'll get them in the order they were received. So a couple questions that we have right now. Let's see here and this is for Angus. So what information is there regarding the concentration of PFAS in cooling towers attributed to concentration cycles?
Bob, I don't have a good answer with respect to quantitative data regarding that. What I can say is that PFAS as fume suppressions will tend to accumulate on the surface of the water, and therefore would also tend to aerosolize. And so in a cooling tower, unlike the mineral phase in the water that tends to concentrate as the water evaporates, the PFAS, the amount of concentration of PFAS in the water could be variable by the fact that some of the PFAS is going to volatilize off. So you may not see as great a concentration factor with PFAS as you would with minerals in water, presuming that in this case that PFAS is coming from the groundwater that's being used in the cooling tower, and that there isn't a reagent added to the cooling tower that contains PFAS.
Okay, thank you, Angus. Next one. What are Stantec's field capabilities and dedicated teams for assessment of PFAS at environmental sites? And I'll turn that over to Krista.
So we have offices across the US and across Canada. So we have great depth and breadth of staff in all parts of of North America, essentially. And in terms of capabilities specific to PFAS, that really always draws out of our PFAS working group. So if we have a project that's PFAS oriented anywhere in the country, we would reach back into our PFAS working group to make sure that those projects are set up and running according to the best science.
And I would just add to that as well, we could do a whole separate presentation on sampling techniques and so forth. And I know another number of companies have done that. So if you want that in the future, just please let us know. Okay, moving on. This one's for Angus. So what are the impacts from the use of C6 foam? And that's the question.
Yeah, so AFFF PFAS transition to C6, and I presume that's what the question is asking about. So this was the hexane or 6-carbon chain length PFAS. What I can tell you is most of the PFAS sites that we've looked at for AFFF, for instance, have a more minor component of what we call the modern AFFF or modern PFAS AFFF that uses the hexane. So we haven't seen a considerable amount of that in the waters that we've been looking at because of the historical use of PFAS, as the prevalent and most commonly used AFFF reagent or PFAS reagent. But what I can say is that sulfonates tend to be less mobile. So the C6 sulfonate used in AFFF would tend to be less mobile than, say, the alkyl acids, so PFOA and the PFHXOA compounds. So you would expect to see the sulfonates accumulate more in soil. As the refinery case study I showed you indicated, you saw PFAS as the prevalent compound in soil versus groundwater, where you would see the alkyl acids and then the shorter chain compounds, presumably also shorter than C6, but C6 as well.
Okay, thank you, Angus. And Krista, back to you. Are Teflon coatings and tapes an issue?
Yeah, it's an interesting question because with all of this evolution of guidance values and screening, it has been very specific to environmental media. We're not really seeing that same response associated with commercial products. We do see obviously the phasing out of those key components, PFOS and PFOA, but the broad use of PFAS. And in fact, if you look at the Toxicity release inventory list, it's got, I want to say, over 166 different PFAS parameters that are clearly part of industrial processes and continue to be. So I would say it's somewhat of an unexplored area, but that said, when we start talking about PFAS in commercial products, usually where people will focus their concern is in the disposal of those products and what it means as that PFAS comes out into waste leachate or landfill leachate. So that is an area that's continuing to evolve.
Great, thank you, Krista. And here's another one for you as well. So with regards to PFAS contamination on mining sites, what, if any, regulation, legislation, and environmental legacy is translating into legal and financial liabilities to hold mining actors accountable?
So I'd say in terms of the litigation that's been observed to date, it's been very focused on the chemical manufacturing facilities. We haven't really seen that translate to the same way to other industries such as mining. So it's not an area we've seen a lot of growth in terms of litigation. There is use of PFAS containing products within various mining production processes, so we know that it could be at those sites, but we haven't seen a lot of regulatory focus on that yet.
Okay, thank you there. And back to you again, I think.
Oh my gosh.
Why are the U.S. health advisory limits more stringent than Canadian standards?
So this wide variation that we see in the different health-based criteria is like they come from a few different things. And usually how it starts is how that agency is deciding on which study they're using to develop that value. So these different agencies will pick totally different toxicity endpoints. So the US value is based on developmental effects observed in rats. And I think the Canadian value is based on liver effects that were observed in rats. So they're picking completely different studies, completely different toxicity endpoints, and then they move to develop their values by applying different uncertainty factors to account for inter and interspecies variability. They might apply different exposure assumptions. They might use different stages of life to develop their values. So they end up with completely different values. That's why you see that big range is there's no consistent process for even starting with the toxicity endpoint we want to use. And then they all evolve their values a different way. So that's why we see that big range.
Very good. Joel, this is for you. So at the NRC site, what steps have been taken to remediate PFAS in the soil and groundwater?
Yeah, thanks. I touched on it briefly, but there's been a couple of interim actions done at that site, and it's still in the process of being investigated. So I'll just say that it's very much a live site at this point too. But the first thing was to remove that source soil. We saw high concentrations in the soil, so there was excavation and disposal of the source soil. The second was protecting the domestic water well risk. And so there were individual carbon filters installed at the domestic residences that had concentrations above detection limits.
Thank you, Joel. Okay, well, that looks like it's it for our questions for today. Please feel free to reach out directly to Krista, Angus, Joel, or myself with any other questions you have or to talk more about your own project requirements. Thank you to everyone who joined today's session. A link of the recording of the webinar will be sent to each of you along with links with collateral information. We sincerely appreciate your feedback on today's presentation, along with any requests for future sessions that you are interested in. Until next time, on behalf of Krista, Angus, Joel, myself, and the rest of the Stantec team, thank you for your time and have a great rest of your day.